So please help me in welcoming Dr. Jeff Van Cleve.
Thank you, John. No, it's a pleasure to be here tonight, and it makes me think of a personal story of the bridges that people build in our lives from one place to another. The way I got to be here tonight is that Jim Houck built a bridge from Ithaca to Boulder for me, where I could work on Spitzer IRS. I later became a Ball employee. I worked on a few proposals, and then after Spitzer was launched in 2003 and commissioned by February of 2004, Len Andreazzi comes up to me and says, I'm project manager on Kepler and we need an astronomer to talk to the customers. Are you doing anything else? And I said, wow, that sounds kind of cool. Exoplanets, that's one of my core scientific interests. And so that's how I wound up working for Kepler at Ball. Then once Kepler was launched, as shown on the right here, I went out to Mountain View and worked with NASA Ames on the commissioning data analysis. And then after 4 years, Kepler was doing exactly what it was designed to do. The same thing over and over and over again, measuring the brightness of stars with great precision. And I thought, great, it's just going to be 4 more years of this. There's a missing part of my career, which is airborne infrared astronomy. So I went over to the SOFIA project, the Flying Astronomical Observatory, and after various twists and turns, I wound up being a flight planner for SOFIA. And I also worked with Ted Dunham of Lowell Observatory. We chased the shadow of Pluto across the South Atlantic, and I figured, doesn't get any better than this. So it's a good time to go. Meanwhile, I heard the story of Kepler transforming into K2, and that's the story I'm going to tell you tonight. And it was so exciting and so different from the Kepler mission that we built and launched back in 2009 that I came back. And it's great when you leave a place or a relationship and then you're welcomed back after a number of years of doing something else. It means that people know that even with all your flaws, you're still welcome and a valuable member of the team. So I just want to give a heartfelt thanks to all the Kepler and K2 people who took me back after my aerial adventure. Thank you very much. So what's Kepler meant to do? Kepler is meant to look for very small fluctuations in brightness as a planet passes in front of a star. This is a very much exaggerated scale. I mean, this looks like a factor of 2 brightness change, but really it's like a part in 1,000 or even 1% of 1%. So if you want to detect planets the size of the Earth, you've got to do that 1% of 1%. And the other thing you need to do is you've got to watch a lot of stars for a long time, because we don't know ahead of time which planetary systems are going to be lined up just right for this to happen. And so we got to watch them all at once. And this only happens over the space of a few hours, maybe over a year. So we've got to take data every 30 minutes for years on 200,000 stars. And that's what Kepler was designed to do, to take data on 200,000 stars every 30 minutes with the ability to measure 1% of 1% of a dip in brightness and have people believe, and this is the important part, people believe that the only likely explanation for what we found was a planet and not some systematic error in our data. I'm not going to talk about how we beat down systematic errors, but as Carl Sagan said, extraordinary claims require extraordinary evidence. And so we had to be very careful with calibration and data analysis. So if we saw a 1% of 1% change, the only remaining explanation could be a planet passing in front of a star. And that's a wonderful story for a highly mathematical audience some other day, which I'd be delighted to talk about at another time. So here's a picture of what we're trying to do. This is an illustration of a Jupiter-sized planet passing in front of a star the size of our sun. So Jupiter's 1/10 the width of the sun, so it's 1% of the area, so you get a signal about 1%. This little dot over here is what Kepler was designed to detect, because the science team really wanted to find Earth-like planets around sun-like stars. And so a goodly number of large planets had been found, but they were not like Earth. They were either much bigger or much hotter. And as someone who works for the SETI Institute, the question of habitable planets is really what's exciting in terms of our place in the universe, though it's pretty cool astrophysics even detecting Jupiter-sized planets. And so the way we figure out whether it's habitable is from two factors: the size of the transit, which gives us how big the planet is, and what is the interval between transits. Because we know in our own solar system, the further out you go, the longer it takes for planets to go around the sun. So we can apply the same kind of thinking to other stars and figure out how far away from the star is the planet and get a rough estimate of its surface temperature. So this is what we built at Ball Aerospace. I've looked at this picture here for years. This is our Kepler focal plane, which has 100 million pixels in it. And can someone from Ball tell me that person's name?
Pat Kelly.
Matt Kelly, thank you.
Pat Kelly.
Matt? Pat Kelly, okay, thank you. I have mistaken it for Joe Manriquez for many years because my ability to recognize people just by their eyebrows is somewhat limited. So that's a long-standing misconception. Thank you, Scott. And here it is in the clean room at Ball during its final stages of assembly. So it's 1 meter across, so it's kind of small compared to James Webb, but it's meant to be wide field of view, 116 square degrees, which by reference is about the size of your palm held at arm's length, while a typical field of view for like Spitzer or Hubble are what you call like 5 arc minutes on a side. For normal people, that's like a grain of sand held at arm's length, because we had to watch 200,000 simultaneously. We couldn't just go from one to the other one because we didn't know when the transits were happening. So we had to watch them all. And so there's a trade-off in optics between having a very wide field of view and a very large aperture, and it costs like beaucoup money to build a big aperture with a wide field of view. So this was the sweet spot in terms of accomplishing the requirements for this size. And it was meant to stare for 4 years at a time because the Earth goes around the sun once a year, of course. But to nail down this thesis that the only thing that this could be, this 1% of 1% change, the only thing it could be as a planet is you want to see it happen 3 times and the interval between those events to be equal. If it's not a planet. And so you had to stare with great vigilance at the same part of the sky. So, it's a success. It met its requirements, lasted 4 years, found all these planets here with orbital period in days. It depends on the star what temperature this corresponds to. But there's like 4,000 planets here, and a recent paper led by Natalie Batalha and Susan Thompson show that most of these, 90%, are likely to be real planets rather than false positives or some other thing. And Kepler was always meant as a statistical mission. You wouldn't bet your life at 3/9 probability that one of these blue dots is really a planet, but you do have very high confidence on this overall total number of planets and the statistics broken down by period and type of star. So Kepler did achieve its mission very much in that sense. So as I mentioned earlier, working for SETI, we think a lot about the habitable zone. Here's a simple way of presenting it. If it's too close, it's too hot. It's in the middle, it's just right. Too far, too cold. Seems kind of simplistic, but it's what we have to start with. And of course, planetary atmospheres have a lot to do with the surface temperature of the planet. For example, the Earth surface temperature would be below 0 degrees centigrade, below freezing point of water, if it was not for the greenhouse effect we already have based on carbon dioxide and water. So, but as physicists and astrophysicists, you start out with what you know. And this is very simple. but we feel we're on more solid ground than cosmologists when it comes to conjecturing our ignorance. So this is where we start. So liquid water is necessary but not sufficient for life. The habitable zone tells us, well, it has to be in here to have a chance of being habitable. We don't know what its atmosphere is, but we know if it's this close and it doesn't even have an atmosphere, it's going to be too hot. So it's a way to just start framing the problem. Otherwise, you just kind of look at the whole Drake equation, wonder why we haven't heard anything. But the genius of Kepler is to break down the search for habitable, intelligent life in the universe, to understand our place in the universe, by breaking it down into a chunk of science that we can do in our own time, and did with Kepler. And so that was our goal. That's what really motivated Bill Barucki, who carried this thing for like a decade, getting rejected 3 or 4 times on a discovery mission. And that was his holy grail, to test, to measure the prevalence of habitable worlds. And so it's important to recognize that the habitable zone is a key part of the motivation for Kepler. And these zones here are set by the amount of heat, of light that comes from the star. It's too cold if it's less than half of what we get. It's too hot if it's more than twice, kind of like Mars and Venus, respectively. So that's where we set the bounds to our search. And that's why we had to stare for all those years, because while it's interesting, and is very interesting, whether there are planets around red dwarfs, which are easier to see because the star is not so big compared to its planet. And it's also interesting to see, oh, there's big Jupiters and Saturns around other planets. We're thinking of our place in the universe. I think Bill was motivated by the question, how likely is it that a world like Earth and a solar system like this one is out there? And so that really drove the requirements, and it's what we were able to do. Here's a close-up of the habitable zone. As I was mentioning before, this is the amount of energy received by the planet from its star. Earth is down here at 1, ratio to Earth. You got Venus out here at the inner edge of the habitable zone, outer edge of the habitable zone. And these are the planets discovered by Kepler as of June of this year. That came out in this recent catalog in this area. So some of these planets are about Earth-sized, and some are bigger. And it doesn't sound like a very remarkable statement offhand, but this is one of my favorite discoveries about Kepler. Long ago, I was in physics, and it seemed when I was ending my time in graduate school, and I do mean time as in hard time, that I was putting myself to sleep trying to describe my dissertation, because it seemed like a lot of physics was putting the 6th decimal place on things we already expected. For example, the Higgs boson, tremendous achievement to find it, but it was predicted in the mid-70s. So not finding it would have shaken the foundations of physics, but finding it leaves us kind of puzzled about where to go next. In contrast, astronomy seems to turn up a paradigm-shattering discovery once a decade or so, like the acceleration of the universe. And then this chart here. This is a histogram of the small planets discovered by Kepler. And before Kepler, there was conjecture, oh, all the planets are big. Well, that was a selection effect, because it's easier to find big planets than small planets. But we had no data down here. And then, remarkably, we found that there are, in fact, more smaller planets than big planets. And here's the kicker. The most common kind of planet that Kepler found is a type of planet which we don't have in our own solar system. Something about 2 to 3 times the diameter of the Earth. Now we have, down this size range, we have Earth, Mars, Venus, Mercury, kind of down here. We got Neptune and Uranus there, Jupiter and Saturn here. But in this interval between 1 and 4, there is nothing in our solar system. And Kepler found that's the most likely kind of planet. So here's another case where our self-centeredness get shattered. And I like that, because we started this 20 years ago, think that, oh, other solar systems kind of look like our own. And two things happened since then. This discovery of Kepler and what's called the Nice model of planetary migration, which explains some of the features of other planetary systems. So instead of the gas giants forming where they are and kind of staying there, there's now this very dynamic model of solar system formation, kind of like worlds in collision, for those of you old enough to remember Velikovsky, where the planets move around, cosmic catastrophes take place. Big gas giants, they have to form in a cold place so all that gas can condense, and yet we find them, many of them, closer to their suns than Mercury in terms of the heat they're receiving. So just in the field of exoplanets alone, there are two startling discoveries, and that's just the kind of thing I love about astronomy. So we have a great discovery, we have mission success, we have a surprise to keep the theoreticians busy for quite some time, and then disaster struck. Kepler has 4 reaction wheels, which are kind of like gyroscopes. And you can get by on 3 of them, because if you got 3 things to spin, you can control your pointing in 3 directions. But a few days after completing its primary mission, Kepler lost its second reaction wheel and began to lose pointing control, which is kind of humorously depicted over here. And then the press kind of picked it up. Major failure, well, yeah, major failure. Hunt for a new mission, yeah, that was a creative response to it. And, well, this one, I don't know what journal that's from, RIP Kepler, NASA gives up fixing the planet-hunting space telescope. And that, I guess that may have been right in a very narrow sense, because there were some attempts to like spin the broken wheel, kind of let it rest, and you know, that worked. So it was in a quandary, and I didn't observe much of this up close because I was over on Sophia at the time, but this story is kind of what started drawing me back to the program. And so offhand you'd say, well, with only 2 wheels, how can you point precisely on 3 axes? And it's was thought to be a very firm rule of precision photometry that you had to have precision pointing as well. Because if the image moves around, slight differences in detector properties, even within an individual pixel, could cause variations in the signal that would swamp what is coming from an Earth-sized planet. So yeah, I mean, for photometry, it's like doom. I don't mention any names, but I was working with some people to think of whether we could use this to look for asteroids or something like that. But something else happened. It was not given up that we could achieve great photometry. And so Kepler was saved by insights from Ball Engineering, especially the ADCS department. The spacecraft has 2 wheels. So what are the natural forces? Well, if you're in a trailing heliocentric orbit, there is really nothing there except the sun. That's why it's a heliocentric orbit. And so the idea came about to balance the pressure of sunlight along the symmetry axis of the spacecraft, so that sort of, but not exactly like, balancing a pencil on its tip, it's quasi-stable. So as long as it stays in that orientation, the torque is minimized, and then the other reaction wheels are spun up to provide a resisting torque. And so it's, the higher those wheels spin, the harder it is for sunlight to push the telescope off its pointing. On the other hand, these wheels have a maximum speed, and wheel life in some ways is dependent on how fast the wheels are spinning. So there was a very judicious engineering decision about how fast to spin those wheels to provide enough torque to make this hard to twist in the sunlight, but not wear out the wheels before we ran out of our other critical consumable, which is thruster fuel. So this is not perfectly stable. It's not absolutely stable. It is like a pencil balanced on its tip in the sense that it will still move, but very slowly, and eventually it'll move enough that we can't do the photometry. We can't collect the starlight that we want, and we will suffer excess noise and won't be able to do what we need to do. And so this error builds to about a pixel every 6 hours, and then is corrected by thruster firings. Just for perspective, Kepler pointing was stable to 1/10 of a pixel over 3 months. K2 is stable to 1 pixel every 6 hours, and yet, because of the cleverness of operations and of data analysis, which I'll talk to a little bit later, we're able to be very productive scientifically. So we can't joystick it because it's 1 AU away, 20-minute round-trip light time. So it's autonomously corrected. Every 6 hours, a process wakes up, squirts a little thruster juice. There are fine guidance sensors that look where the guide stars are, and more than 90% of the time, you're back in business, and you only lose a few percent of the data while the spacecraft is being repointed. It's an interesting observation from Charlie Sobek that the amount of force required to unload this roll error is so small that they're not using thrusters directly, they're using opposing thrusters. And maybe someone from ADCS in the audience could confirm that's true. It's kind of startling. Caitlin, is that really how it works? That's really how it works. And so just kind of built in, I mean, these weren't designed to be mismatched, right? Usually this stuff is like, okay, how many newtons or whatever. And so it's just kind of an accidental feature of the as-built thrusters that allows this to happen, which is pretty cool. Of course, we're not distilling our own hydrazine up there, so eventually we'll run out, maybe a year from now. And I'll talk a little bit more about that in detail later in the presentation. Meanwhile, there was drama at the Ops Center because we have to operate the spacecraft in an entirely different way. Using the solar pressure, devising sequences that kind of wake up the thrusters precisely every 6 hours, so these thruster firings are synchronized with the data collection, thus minimizing the data loss. Saving the engineering data, fault logs. I mean, we're operating this thing that was never designed to do this, and so this engineering data is extremely important because you try something new with a highly engineered product like this, the odds of something unexpected and possibly fatal happening are not inconsiderable. And so it's really important that the Ops Center here at CU figured out a way to save these sequences, the engineering data, fault logs, even while Kepler K2 is getting further and further from the sun. Again, not a circumstance that was ever anticipated. In this next bullet here, they adapted operations to the lowest uplink and downlink rates ever used. I think we're contemplating something like 10 bits per second, which even for people old enough to remember dial-up is much slower than that. And it also means using the antennas in a way that were never designed. We're almost 90 degrees off the main radiation pattern of the low-gain antennas when we're collecting this data so that we can collect engineering data while we're collecting science data. It's pretty incredible when you think about it. So now we have a working spacecraft that's doing something very different from what it was designed to do. And one fundamental difference is because we're using solar radiation pressure, we have to point the telescope in the ecliptic, that is the Zodiac for the astrologically inclined. And so we can't point at that same field in Cygnus where we looked for 4 years at exoplanets. And so this was kind of a philosophical moment because Bill and the science team that got Kepler to happen, followed it, pressed this with like an Ahab-like determination that we were going to find Earth-sized planets and sun-like stars, and now that's gone. And while Kepler achieved its primary mission of 4 years, the stars turned out to be more noisy than were expected. It turns out that the sun is actually a fairly atypical sun-like star, which astronomers like to say things like that. And so, to quote Shakespeare, the fault was not in ourselves, but in our stars. And the science team wanted to look another 4 years because the noise was 40% higher. It's kind of a square root of time process. If we could have gone 8 years on Cygnus, we could have achieved our original sensitivity, our original planet yield. And the science team voted to look another 4 more years at Kepler when they were talking about an extended mission, but that's not what happened. And so K2 can't do this, and so people started thinking, we have a precision photometer, it just has to look in the ecliptic at a different place every 3 months. What can we do with it? Well, you know, even though K2 is twice as noisy as Kepler, it still makes it 10 times more precise than anything that can be done from the ground. The best literature I've seen on optical photometry, doing this kind of work from the ground, is a few parts per thousand. Now, parts per thousand sound pretty good until you realize a part per thousand is 1,000 parts per million. And so from the ground, you can do 3,000 parts per million. Well, Kepler was designed to detect 1% of 1% at a factor of 5 signal noise. Well, that's 20 parts per million. So 3,000 parts per million from the ground, 20 parts per million from Kepler. And even with the roll noise, it's 40, 50 parts per million as the noise figure. So it's still incredibly great photometer. You just have to kind of think of other things that are interesting to look outside, you know, the paradigm that the science team followed for all these years. And we have this great instrument, and the cost to operate it per year is less than 3% of what it cost to build it in the first place. So it seemed kind of tragic to throw it out just because it couldn't accomplish its original science goals. And so a lot of smart people thought about this and came up with some great ideas. This graphic here is made by one of our artists on Kepler, Wendy Stenzel. So this is called the K2 medallion. And what it does, and I love this because it combines astronomy and astrology, just like Kepler himself. You see the signs of the Zodiac in the middle here. We're compelled to point at the ecliptic. And then you see different kinds of targets that we'll look at around here. And it's a very diverse bunch. Here are the original goals of Kepler's exoplanets and Astro seismology, which is telling from the light fluctuations of stars, kind of like starquakes, what the interior of stars look like. Kind of like earthquakes tell us what the interior of the Earth looks like. And this was intimately linked to that because the signal we get from a transit is the ratio of the planet size to the star size squared, ratio of their areas. And if we don't know the size of the star, we don't know the size of the planet. So how can we say we're looking at Earth-sized planets? We can't. Measuring the frequency of this oscillation here tells us how big the star is. And so then we know how big the planet is because we've measured the planet to star ratio. But many other things came up. Objects in our solar system, which is an incredible headbanger topic, nobody talked about when we were doing the requirements flow down indoors. There was nothing in there about solar system objects. And this delights me because that's one of my principal interests along with exoplanets is our own solar system. So K2 does that. Active galactic nuclei. Oh, young stars, exploded stars. We can look at entire star clusters because of the large field of view. Planets that are vaporizing, clusters of galaxies. I mean, people just stare out into the abyss looking for supernovas. Stuff falling into black holes, and our galactic center. And then my favorite topic here, the unknown. This is what's called a full frame image that collects all the pixels instead of the 3% we deem to be most scientifically interesting, but you know, that's 97% we're not looking at. And so I like the idea that we do snap a full picture once or twice every season to see what's out there. This next slide shows one of the things I like the most about K2. a lot of young people were brought onto the program in the guest observer office. And this is their way of showing what K2 is about. And I think it captures the spirit of playful improvisation on K2 instead of a very NASA-like process of here's the mission requirements, here's the flow down, this is the science goals. It's like, oh, well, let's think of some stuff to look at. That's really cool. And then like visualize it. And so here are some of the topics I talked about, with the medallion, the supernovas, planets with multiple super Earths around them, which are these kind of planets that we don't have in our solar system, brown dwarfs, and this is kind of in order of distance. So here's our Earth and Sun, and it's not to scale. None of this is to scale, but I just love the kind of cartoonish playfulness of it. And you see here's some asteroids and trans-Neptunian objects and Saturn, comets. Who've done all this stuff, and it's just been wonderful inventing on the fly what's interesting to do and then doing it. And so I really like this. And it says start, and so 2017, that's for particular field 15. That's just for one field, so that's our campaign 15. But the younger folks, they have a great time on this program, and that's one of the things most satisfying to me. So Kepler was about one great goal, which it achieved by and large. And we planned what Kepler was going to do years ahead of time. It was a fixed target list. We did target planning, and by launch time, we pretty much knew what 200,000 stars we were going to look at, and 4 years later, 80% of them were still on the target list. And I want to point out, monotony may sound pejorative, but it was actually required for Kepler to do its job. It had to do the same thing over and over and over again, exactly the same, so that we would have high confidence that these 1% of 1% changes were due to planets and not Kepler kind of just doing its own thing, kind of different. And so that's really important to keep in mind. And we kind of lucky in a way that this happened halfway through the 8 years that we're going to be operating this, because we had just enough time to accomplish our mission here. It's a lot of fun flight planning for K2. It's a little quirk of my career that I was a flight planner for Sophia, and now one of my chief roles on K2 is flight planning. I love math problems that are operationally essential, because then I find them interesting, but they're also important to the program. And so I kind of really fit into this role coming off of Sophia as flight planning. So the scientists figure out what they're going to look at, and I figure out which of the 100 million pixels those targets correspond to, even for the moving targets. And so, but it's a brisk pace, because every 3 months it's a new target list, and not only is it new targets, it's new kinds of targets, not just stars of 12th, 10th magnitude, but like really bright stars some people like to look at. Stars so bright you can see them with the naked eye, which presents its own problems with a space telescope like this. Solar system objects, galaxies, star clusters. So we had to write MATLAB tools on the fly to prepare these target lists. And we've really struck a great balance, because I mentioned the NASA way of doing things, and that's actually really important in some contexts, because we have a core to our software where every change has to be documented, approved, discussed, but we can count on that core being stable. And around that core, we just make up tools on the fly to feed that core program that calculates which pixels we're going to ask for. And we can make mistakes, and we can debug them, and this can all happen in the space of a few days. And so we're making stuff up as we go along, but part of that is we can count on this very stable, well-controlled core of NASA software. So I think it's a really great symbiosis between flexibility and stability, which a lot of software development organizations find very difficult to strike. But I think we've done a great job on it, on K2. And here's just a nice graphic showing here's Kepler staring at Cygnus, this one place here. And then K2 goes along the ecliptic, and there's our galaxy, probably a picture from Spitzer or something like that. So it's worked out quite well with the flight planning. So after we analyze, we collect the pixels, then we have to analyze the data, and of course there's a lot more artifacts in it than we had in the original mission. And one of the great things about K2 is that the data analysis software paradigm is similar in many ways to the flight planning paradigm, in the sense that there is this rock solid core of NASA software that reduces the data to a high enough quality to see if something interesting is there, while at the same time the community invents its own tools that are tailored to work best depending on what they are looking for scientifically. So as someone said a long time ago, we have let 100 flowers bloom and 100 schools of thought contend when it comes to the data analysis. And well, there are 6 of these high-end data products, and 6 is about 100 cosmologically speaking. So it's been quite remarkable. These are all available on the archive web page. People have contributed what are called high-level science products. And Scott Fleming at the Mikulski Archive said that they've been very popular downloads even compared to mission-produced light curves. And so each of these people have different ways of looking at the problem of how to deal with the large roll errors and the effect on uncorrected, uncalibrated photometry. And then based on what they think is scientifically interesting or their mathematical aptitudes, they've come up with, as of the 12th of September, 6 different add-on data products that are publicly available. So let me show you a little bit about what our NASA pipeline copes with and what our users take from there. So in the blue here is the brightness, the flux of an uncorrected light curve. That's the total amount of light in the pixels corresponding to a given target. That's how bright it is. So every 6 hours, there's a sawtooth pattern, because then the telescope rotates and then the image moves around in this little aperture that we defined for it. More or less light gets in. And if you look at this scale, that's 1.76 something or others, and this is 1.762. So that's a part per thousand there. And that would be great on the ground, but it's fatal for doing exoplanet work. And then our NASA pipeline takes this and flattens out to that, because what it does in a nutshell is it looks at all the stars' data. And if all the stars are doing this, they can't possibly be really doing that all at the same time. They're thousands of light years from each other. And so what our systematic error correction software does is look for patterns that are common to all the data, says this can't possibly be a natural phenomenon, removes those patterns and leaves behind a corrected light curve in a way that is protected against removing transits. The transits aren't happening everywhere either. They happen on an individual basis. So the pipeline is maybe not the best analysis for any particular science, but it is essential to have good browse quality data produced with traceable software and algorithms that is good enough to let people see if it's worth investing their effort to take on their own software and do a better job than our pipeline. So it's a great way of things working hand in hand. Again, you get the rock solid NASA software as the core, but then people are free to innovate around the edges and interact with that software. Because it would be chaos if this was all user-written software. We'd have a devil of a time even believing published scientific results if everybody started out from raw pixels and then had to communicate with each other just what they had done. And so a final word about the pipeline. It's really a massive intellectual achievement that's involved 20 years of thought and programming. And there's 570,000 lines of MATLAB code. How do I know that? I did a find star.m pipe word count -L, and 570,000 came out of my code pile. And it's a tremendous achievement to even keep that much code organized. It's about the amount of code it takes to fly the space shuttle back in the day. And so there's a paper by John Jenkins that kind of leads us through that process of algorithm development. And this is just a screenshot from GitHub. After a long process, this was approved by NASA for release. And Maura here in the audience was one of the key figures in that, because how do we know that none of these 570,000 lines of code constitute an export violation? So, well, that's maybe a talk for another day. But at the end of the day, you can see this was done, NASA approved it, and people can download the source code, maybe not to run it, but just to understand what we did. You know, if someone comes back to this in 10 or 20 years, or even 5 years for the test mission, it's there. So I've talked about how we collect data, how we reduce it, and now it's time for the scientific results. In the first 4 campaigns of K2, we've continued to discover exoplanets, and it has the same histogram showing these super Earths, as was found by Kepler. And this was from a paper by Ian Crossfield. And this scatter plot here shows in gray Kepler's discoveries, and then in these warm tones here, the K2 discoveries. And the color here is the surface temperature of the star, because if we want to understand this, we want to know what's different about, say, red dwarfs or sun-like stars. So some of the planets here, highlighted in this light aqua color, are both in the habitable zone and are Earth-sized. And so we have been getting a few of those. One interesting feature of K2 is that K2 stars are typically brighter than Kepler's, which means that more follow-up observations are possible, either from the ground or from James Webb Space Telescope, or in the fullness of time from WFIRST. We also characterized a multi-planet system that had like 7 planets in the habitable zone, or even kind of close to the habitable zone. Up here, it's called TRAPPIST 1, probably by somebody who'd like beer. And you see that it's the same color code as that slide I showed earlier. Red's too hot, blue's too cold. So there's like 4 planets in the habitable zone and a couple close to it, and they're all like Earth-sized or super Earth-sized. Now, in all fairness, this was found by the Spitzer Space Telescope, but K2 greatly refined and expanded the results. And this plot here is from Luger's paper in Nature, showing the light curve, and then all these little markings here are these planets, of which there are 7. So one of the interesting behavioral aspects of this is how eager people are to publish our data. This paper was submitted and put on the archive server within 5 days of raw, look at that, raw cadence data release. So people are just standing by with their software waiting for the balloon to go up at mast, that the data is available. And so the data, the raw data, not the pipeline data, was available on the 8th, and the paper was submitted on the 12th. So, you know, I can't think of a better example of scientific zest than this. So, as I mentioned before, one of the goals was to listen to what you might call the music of the spheres. Not actually sound, but the fluctuations in brightness have a harmonic content to them, which you can analyze to figure out how big is the star, what's its internal structure look like. And so Bill Chaplin, one of my colleagues at the University of Birmingham, said that just as archaeologists reveal the past by excavating the Earth, we can use the sound in stars to perform galactic archaeology. So this gives us ages of stars, and the way it does that is it tells us the composition, and from the mass and the internal structure, we can tell how long it's been cooking hydrogen into other things and estimate the age of the star. So, you know, this is great science, but it's also kind of cool to turn the data into things our human ears can hear by turning the sampling rate up by about a factor of 100,000 or so. So let me give you a little example of this. This is from Andrea Emilio of Birmingham, and it's from their paper about Astro seismology of stars in the cluster M4 with K2 data. And off to the right here are the labels of the stars that we're looking at. And so it doesn't show up in very good contrast here. These are kind of reddish, but this is a big circle, this is a relatively small circle, and this little yellow dot is the sun. And so one corresponds to that star, and so on. And so I'll just draw these circles with my pointer because the contrast went away here. And then I'll play a little stellar music. So here's the biggest one, number 1. Sounds like a great lumbering beast. Number 3. Number 5. You notice the bigger the star, the lower the frequency. And that's, in a nutshell, that tells us, well, let's hear the highest frequency one, number 8. So that's the smallest star, highest frequency. So in a nutshell, that's how we can tell the absolute size of stars and therefore the absolute size of planets. Another thing that K2 has done is gravitational microlensing, where gravity bends light, just like in the famous 1915 eclipse observations that established general relativity. And so there's a star called the lensing star, and it might have a planet around it. And so starlight comes by the star and planet and gets bent. If there's just a star, you'll just see one spike in the light curve as this lens passes in front of a background star, much more distant. But if there's a planet, there's an additional spike in the light curve. Right here, this is an example from K2 that shows that you can do this science. This is not actually a planet detection, but if it were, there would be a little spike on that shoulder. And you know, even if we don't find a lot of planets this way, this is a great rehearsal for WFIRST, one of which main goals is the detection of exoplanets by gravitational lensing. And you might say, well, what's the big deal? Kepler found planets. What's different about this is this technique is more sensitive to planets further from their star than Mars is from Earth, while Kepler is sensitive to planets closer to their star than Mars is from Earth. And so WFIRST's exoplanet mission will make a wonderful complement to it, and to give people test data from K2 to contemplate what they're going to do with WFIRST data, I think is a great exercise and one of the things that K2 has done. And I said I kind of thought some of the solar system stuff was really interesting. This is a pattern, this pattern here, the rectangles here, that's our focal plane, and the blue arcs show where Trojan asteroids move during the course of a 3-month campaign. And so people in the community have figured out how to deal with data where not only is the telescope moving, but the target is also moving. And so these authors here have figured out how to create apertures that move with the target and do precision photometry of Trojans, which are really interesting because people think the Trojan points are kind of a dumping ground for primitive bodies that might tell us something about the early solar system. And recently the Lucy Discovery mission was approved to go out there and take a look. So this is very complementary to an approved interplanetary mission to go study the same objects. And you might say, well, I mean, you could do this from the ground. You're only interested in 1% or 0.5% photometry. What you don't get from the ground is uninterrupted coverage for 80 days at a time. And that's essential because you got an object that's moving and spinning and if you can only observe a few hours a night, it's very difficult to stitch that together in a light curve. You just stare for 80 days at a time, no sunrise, no clouds. Even 0.1% photometry is incredibly valuable, even though in theory you could do that from the ground. You just don't have the time continuity that you have in K2. So one of the things that I enjoy as a flight planner is designing apertures for moving targets. And so just before I took over this task from Steve Bryson, we looked at our data on Pluto from Campaign 7. And so the set of pixels that we requested is this parabola here. And during the course of the campaign, Pluto moves through this parabola, kind of like a bowling ball going down a bowling alley. Now, a few months ago, maybe a year ago, someone said, well, it kind of looks like that's a little close to the edge there, not in the center. Yes, the path is off by 1 pixel from the center of the lane for mind-numbing reasons. However, since this is a technical audience, I will tell you that I've worked on 5 flight programs in my career, and every single one of them has had an argument about whether your indexing starts from 0 or 1. And so, from the laughter, I see I need not explain in any further mind-numbing detail, but it just amuses me at this point in my career how it's always the same stuff. You count up from 0 or 1, where do we get a world coordinate system, and what does the timestamp mean? Every single program. I love it. It means I can apply what I've done on previous jobs. This is an excerpt from a presentation given by Tom Barkley last year, who is the guest observer officer, now succeeded by Garrett Berenson. And they found evidence of a disintegrating planet. We found these light curves that came back at kind of regular intervals, but the shape was very irregular and changed from time to time. So last I heard about this science, that was the leading interpretation. So you have this, it's not a Kepler measurement here, of course. This is an artist's interpretation, but you have this bright bluish-white dwarf here, and then blasting chunks off this planet that's gotten too close to it. And that's a kind of a cottage industry with K2, is learning about white dwarfs. And that's one of the things they found. K2's also found supernovas, and usually you find supernovas after they happen because no one's looking at the star all the time until LSST comes online. But K2 captured a supernova that happened in 2015. This is an image from ground-based astronomy. But what's really cool about this is Kepler was looking at the same time. So this rise here is full of fun astrophysics, which I'm sure people will talk about more. And that's the kind of thing we're able to do. There's also an interesting sociological feature of K2. I mentioned the young people in the guest observer office. Garrett prepared this histogram of publications, number of papers versus seniority of lead author, by which you mean years since PhD. So there's a lot of papers being produced by young people, postdocing or junior faculty, and people are getting hired as faculty. And I'm sure you all know the nightmarish competitive environment for getting on the faculty of a good university. But it's working. Young people are establishing great results on here. Andrew Howard is not on this list, but I mentioned him by name as someone 20 plus years younger than me that's really done some great work. And then out here, there's the older people and the really older people. I'm actually in this category myself. I've been working in this field since 1990 when I started with Jim Houck on the Spitzer IRS. But what gives me great satisfaction in my work is to see that young people are picking this up with enthusiasm. Down here, it's not just some cottage industry that dinosaurs have been working on for 20 or 30 years and, doing their data analysis in Fortran 77 because, that worked 30 years ago, it works now. So I love the innovation and the fact that it's getting young people started on their careers in astronomy and aerospace, potentially. So we're having so much fun, we have to ask ourselves, when's the party going to end? We're not making propellant out there. Kepler is getting further and further from the Earth in this kind of Earth-centric rotating coordinate frame. And so Kepler's kind of had its 1 AU party a couple of weeks ago. It's about 1 astronomical unit from Earth. Ball's gotten more efficient, but there's only a finite supply of fuel. They're not designed to work at such low pressures, but you know, people think about these with great detail and can really coax some real tricks out of stuff that was never designed to do this. We expect to lose control of the spacecraft sometime between February of next year and November of next year. I'm working on the flight planning for campaign 16, which starts December 7th and goes on for 3 months. And one interesting feature of that campaign is Earth will be in the field of view. So if all goes well, in early December, we'll take one of those FFI images and all wave to it as kind of a parting shot. It's kind of the pale blue dot moment of K2. So we're getting further from the Earth, and yeah, it will end, but it will also have gained 4 more years of productive life. So these are some of the things that are coming next. The TESS mission, some of which is going on at NASA Ames in terms of data analysis. It's being led by George Ricker at MIT. And this too is complementary to Kepler. I mean, this is looking at a different space. Instead of 1 big telescope, TESS has like 7 small telescopes, and so they can cover 700 or so square degrees at a time. And their goal is to chew up the whole sky. And what's great about that, that's that element of surprise I mentioned before. It's not just the targets we know of, but as Mr. Rumsfeld once said, the unknown unknowns that will come out in the test data from this kind of approach. I think it's wonderful. JWST is, as far as I can tell from their webpage, still on track for 2018. There was some concern with the floods in Houston, but I think people down there took care of themselves first, of course, but they also took care of the hardware, so I'm not aware of any trouble arising from the recent natural disasters down there. And so this will do spectroscopy of some of the exoplanets. And W1, which is around the 2020 time frame, will also have a coronagraph in it that has some low-resolution spectrographic capability. Not enough to measure Doppler shifts, but it's enough to tell you, is there Rayleigh scattering? Why our sky is blue? It could detect methane in a spectral resolution of 70 spectrum. Great stuff like that. And Ball has a big part in the James Webb Telescope up here, and may come to have a significant part of W1. And then our European colleagues are going ahead with something called Plato. You see there's 7 telescopes there, and I think each of these little horns is one of its own telescopes. So it's like TESS on steroids. But the appetite for this kind of data seems to be unrelenting, and it's very personally satisfying because this is one of the topics that brought me into astronomy from physics a long time ago. So conclusions are that after being close to death in 2014, the Kepler spacecraft has returned to being a high scientific productivity mission. I would say as productive as the Kepler mission, if the proper weighting factor for diversity is included in it. And Kepler's different way of doing things brought forth new targets, new methods of data analysis, and to me, most important, new people with new ideas about how to best use the instrument. And so thank you very much for inviting me here to talk about this journey from adversity to diversity, and I'd be delighted to take a few questions if there's time and interest in that. Thank you. Yeah.
Have you seen any detector degradation? And what is the general variability of the detectors before?
Well, we've seen entire focal plane modules just die, so that's an extreme form of degradation. We have 21 of these focal plane modules, and we lost one in the primary mission in 2010. Another died between Kepler and K2, and last summer a third died. But that still leaves 18 out of 21 functioning, and there seems to be no accelerated rate of failure. In terms of dark current, read noise, charge transfer efficiency, my colleague Doug Caldwell will talk about that in detail tomorrow, but the bottom line is for K2, none of these detector properties have a significant impact on noise compared to rolling by 1 pixel every 6 hours. So absent catastrophic failure, the detectors are holding up very well. They were built for us at E2V and lovingly hand assembled to their mounts at Ball by Mark Hanna and other people. So that's a tribute to the craftsmanship all around there, that those many are still working.
Again, thank you very much, Jeff.
All right. You're welcome. Thank you.